and introductions. We're going to move ahead with showing you some of the activities that are available on the Nspired website, particularly because the focus tonight will be looking at some activities involving Algebra 2 lessons and Precalculus lessons. After that, I think we go back to Eric, if I'm not mistaken, and he'll discuss some of the online resources that you can access to get more information, and a brief overview of some upcoming events that may be of interest. Next, I guess, I think it's Ray's turn to talk about expectations.
Yes, so some of the activities that we'll be showing you are called action consequence lessons. So we hope that you'll be able to see how these work in the classroom. The idea is that a student actually operates on a mathematical object or takes an action on a mathematical object and then sees the consequence, and from this starts to understand the mathematical object and the concept at hand. And of course, one of the great and powerful things about these documents, Nspired documents, is that they're very interactive. The different mathematical objects interact with each other and with the student. We also hope that you'll be able to find out where to locate other lessons, and there are just a vast wealth of resources at education.ti.com. And then we'd love for everyone to be able to stay in touch with social media, and there'll be upcoming events and other webinars.
Great. And so as Ray shares his desktop, and we'll be focusing on the teacher software here, and as he does that, the right side of your screen has now disappeared, but to access the Q&A window, you can hover at the green tab at the top of your screen. It says Viewing Ray Barton's Desktop, and if you hover over that, you'll see that there's the Q&A window and the chat window, or the icons rather, and you can click each of those icons and access the Q&A window and the chat window. And also, if you click the participants window, and you can minimize these windows so you can fit all three to the on the right side of your screen. But if you click the participants window, in the lower right-hand section of that window, it looks like it's a drop-down menu with a checkbox. And if you click on that menu, it gives you a couple of feedback options. So you can tell us if we're going too fast or too slow. You can applaud and laugh as you wish. It's all electronic, and it's a nice way for us to see how engaged everyone is. So thanks a lot, and she's all yours, Ray.
Thank you. The first activity that I'd like to show you all tonight is called Modeling with a Quadratic Function. And as you can see from this document, you can embed pictures into a document and then act on those pictures. And so we see someone shooting a basketball, and the shape of the trajectory of the basketball is quadratic. So I'm showing you this activity on my teacher software, but it would look just like this on a student's handheld device after they loaded this document and started interacting with it. If we move to the next page, the picture is a bit more faint, and we're going to start following some instructions that are on the student document to try and find a parabola that fits the trajectory of the basketball. So there are some PDF documents that come with these activities, and this is the PDF document that comes with Modeling with a Quadratic Function. That is a blackline master that you could hand out to the students. And so the activity is intended to be somewhat independent. Students could work on this at their own pace. So here are some instructions for the student. They're first asked to graph the parent quadratic function f at x equals x squared on page 1.2 of the document. And then we're going to transform that equation and that graph so that it fits the trajectory. So I'll go back to my document, and function entry line is open at the bottom of this screen, so I can just type in the equation x squared, which is showing up at the bottom, and then when I press enter, we get a parabola, but of course it's nothing close to matching the trajectory of the basketball. But this graph is draggable, so if I hover the cursor over part of the graph and get this slanted icon, it means I can stretch or shrink the parabola. So I'm now clicking and dragging, and I can change the parabola until it's concave down. And then if I move the cursor until it's hovered over the vertex or someplace close to the vertex, I get an icon that looks like a four-way arrow, and that tells me that now when I click and drag, I'll be able to shift or translate the parabola. And as you do that, you see that the equation updates automatically to match the transformations that I've made in the parabola. So I'll just play with this a little bit more here and see if I can get a pretty good match. And students will be able to do the same thing with their handheld device using the touchpad on the handheld. So this is not too bad of a fit. And I'm going to drag the label so it's out of the way. And then there are a few other questions in the document that students might want to answer using their newfound equation. For example, determine the maximum height of the basketball here, question number 3. And there are a couple of ways that a student could do this. One might be to actually trace on the curve until we reach the maximum point. So that's what I'm going to do. So I'll press the menu key and then select option number 5, trace. And then I'll do graph trace. And now we get a cursor that appears on my curve, and I can move the cursor around using the arrows on the touchpad. And notice as I pass through the maximum, I'll go back through it again, a little pop-up window appeared that said maximum, and you can see the coordinates of the point down at the bottom of the screen here. So it looks like it reaches a maximum height of about 8.66 meters. Actually, I think the scale here, I think the document said the scale is 2 tick marks for every meter, so we might cut that in half to get the actual height. And there are some other questions that are asked. For example, how far does the basketball, would the basketball land from the shooter if the basketball rim weren't there? So you could follow this trajectory on down until it hits the ground. And when we get there, notice another pop-up window that says 0. So it looks like it's the coordinate is about 16.3, 0. And again, I suppose we would divide that number in half since it's 2 tick marks for every meter. So it's 16.3 tick marks, which means about 8 meters away. So in each of these documents, these activities that you download from the Math-Inspired website, there's typically an inspired document like this one that I've been illustrating, and then also the PDF document for the student. And there also is usually another PDF document with the title Teacher. So let me just show you that one for a moment. So this one still says Modeling with a Quadratic Function, but it's Teacher Notes. And this has some objectives, vocabulary, coordination with different standards. And then down below, we've got some tech tips that might be helpful for the teacher to point out to students. And then here, the same instructions that the student sees, but also some sample answers. So the teacher document has some solutions and possible answers that students might come up with. So I don't think we'll show too many more of these documents, but just wanted you all to know that with each of these TI-Nspire activities that we're doing, there's lots of documentation in the form of PDF documents and Word documents for both the student and for the teacher.
Great, and thanks, Ray. And we have a couple of questions about this activity. Let's see. Derek has a question about the slanted arrow. So when you were transforming the parabola, he asks, let's see, what does the slanted arrow do, and where can it be found?
So I think we're referring to this slanted arrow that you can see on my screen now. When I move the cursor until it hovers over the parabola, then it changes into this slanted arrow. I hope that's what Derek's talking about.
Yes, I think it is.
And if that's the case, what that's telling the user is that now if I click and drag, I can change the, it's a stretch or shrink factor, so it's a horizontal stretch or shrink for the parabola. and then when I let go or press escape, then I'm done stretching or shrinking the parabola. Whereas if I move the cursor and hover over the vertex, then I get this four-way arrow, which means that when I click and drag, it will translate the parabola horizontally or vertically. So the shape of the icon is just a cue to tell you what's going to happen when you click and drag. So this way you can tell whether you're going to be translating the graph, or if I'm over here on either side, then when I click and drag, I'll be stretching or shrinking the graph.
Great. And all you were doing was hovering your cursor, right? You didn't have to go to the menu or anything?
That's right. There's no need to interact with the menu. I just move the cursor, and as soon as it hovers over the graph, then the icon immediately changes to this slanted arrow. And then I can just click and hold down the clicker and drag, and then it will start changing it.
Great. Thank you. And we have one more question about the handhelds in the image here. So let's see, Peter asks, we have the Nspires that are monochrome. Will we still be able to use this activity?
Great question, and the answer is yes. And I think if I change this in the teacher screen, I can show you what that would look like. Let me go to the one that's a little has a little more color. If I click this icon over here, I can change the view to what you would see on monochrome. So that's what it would look like on a touchpad, or even on the older click pads, the gray and white machines or the blue and white machines. So you'll see the same picture, it'll just be in black and white.
Great. Thanks, Ray. And if you have any trouble downloading this activity and transferring it to your handheld, and if you do not see what Ray just showed us, chances are you might need to update your operating system. And towards the end of the webinar here, we'll show you some video tutorials, and one of those video tutorials is on how to update the OS. So thanks, Ray.
Okay. So I think we'll move on to another activity. This one is called the painted cube. It's also it's an Algebra 2 activity, and it's a good way to get students conjecturing and looking for patterns and interacting with another mathematical object. So the initial question that is asked is, suppose you're given a 10 by 10 by 10 cube and you dip it in a can of paint. How many unit cubes have paint on perhaps 0 faces? Or you might ask the question, how many unit cubes have paint on 2 faces or 1 face or 3 faces? And we'll start out this activity by using a good mathematical problem-solving approach of reducing the problem to something a bit more simple. So if you go to the next page, instead of a 10 by 10, we start with a 2 by 2 and answer some of those same questions. And over in this side of the window, it's a split screen, and on this side, if I drag these circles, then I can change the orientation or the rotation of the cube. And it moves just about this fast on the handheld, too. So it helps to get kind of a visualization of the problem, and we start to see what would happen. And go back to the question again, how many of these cubes would have paint on, say, 1 face? Well, here we can see there aren't any. As a matter of fact, there are 8 unit cubes that make up the larger cube, and each one of these has all 3 faces with paint. So 8 cubes have 3 faces with paint. And then I think we ratcheted up on the next problem. So I clicked on the tab up here to go to problem 2.1. And now this cube is a 3 by 3. And again, you can rotate these, rotate the cube, change the orientation by spinning these arrows on the side here. So this is a nice document that someone has programmed for us to use. That's the nice thing about Nspired and the education.ti website, is that there are all kinds of pre-prepared documents that talented people have made, and it's easy to just download these to students and let them start playing with them. The next page states the question that was asked about an n by n by n, and then on the next page we can start filling in some of our answers here. So notice that for a 2 by 2 by 2 cube, every face had 3 sides, or every cube had 3 faces with paint. So I think the answer would be that all 8 of the individual unit cubes have paint on 3 faces, and there are no cubes that have paint on 1 face or 2 faces or 0 faces. And we won't spend too much time going through all the details, although it's kind of a fun problem to look at. But we could look at the same thing with 3 by 3 by 3. There isn't a page with a 4 by 4 by 4 cube to look at, so students would have to start drawing their own or start trying to figure that out. But the idea is that they would fill in the rest of this table, and as they do that, we'll be able to visualize each of these data sets on the next page. Because there are some scatter plots that are set up. So what I'm going to do right now is just jump to the solution document. So not only is there a student Nspire document in this activity, there's also a solution document that might be helpful for a teacher. And so I just switched to the solution document that has all of the answers. And now if I go to the next page, for example, this is a scatter plot for different size cubes and how many faces have, or how many cubes have 2 faces with paint. And we see that it looks like it's linear. So the column that we're looking at is this one right here, column D, that says 2. So we're plotting these points. 0, 12, 24, and 36 are the y coordinates. Of course, and the first column N, that's the x coordinates, 2, 3, 4, and 5, that's the horizontal. And then column D is the vertical. And so then in the activity, in the black line master activity, students are asked to see if they can find the equation of this scatter plot so that they can then make a conjecture about, a generalization about how many unit cubes have 2 faces with paint, if you know N, if you know the size of the overall cube. So my goal right now is to get a line fit for this scatter plot. So if I click on Menu and then go down to Analyze, there are 2 ways to get a line. One is to add a movable line, and the other one is to sorry, I clicked the wrong one there. Let me go back a step. The other one is a regression line. So I'm going to select add a movable line. And this is kind of like the parabola that we saw in the basketball activity. This line is movable. If I put the cursor here in the middle, I can shift it. And if I place the cursor out over one of the ends, I can rotate it until I get something that's pretty close. So I've got a line that's 12.4x minus 26. If I wanted something that hopefully is a little more exact, I could add a regression equation. And I'll choose a mx plus b form for the regression equation. And then that does least squares fit. So 12x minus 24 is the equation that might help me to predict how many unit cubes have 2 faces with paint. So to answer the original question, if it was a 10 by 10 by 10, hopefully we could put 10 in for x and get the answer. Any questions come up on this one before I move on to the third activity?
We had a question from Misty, and Judy answered it, but we'll go ahead and ask it verbally here. Are these activities available online?
Yes, they're on a website called Nspired, and Eric is going to show us that website towards the end of this webinar. He'll show us where some of these activities are. All of the activities that we'll be demonstrating tonight come from this same website, and Eric will show the website and also perhaps show you how you could download one of these activities.
Yep, we'll definitely do that towards the end. Thanks, Ray.
You're welcome. And I'd like to just show one more activity before we hand this off to Howard, and it's called the Airport Impact Study. And this is an activity that could be used to study inverse functions, inverse variation functions. Again, there are PDF documents that accompany this, but the nice thing about the Nspire documents is that you can put a lot of documentation right into the document that is sent to the students. So students could actually see these instructions on their handheld device. So the problem setup is that there's an airport and we're concerned about noise levels. And so we're trying to find the relationship between the distance away from the airport and the noise levels. And so we actually have a sort of an interactive model coming up on the next page, not this 1.3, but on page 1.4, where we'll simulate this process of collecting noise data at various points around the airport. And so we're going to be moving a point around, and when we get the point to someplace where we'd like to draw a sample, we'll press Control and then the decimal key, and it will collect that data set, or that ordered pair, and put it into a spreadsheet. So hopefully this will make a little more sense as I demonstrate on the next page. So the noise source is down here. This is the airport, and here's where the measuring device is that's measuring the sound intensity that's coming from the noise source. And I can move it around horizontally by dragging this red hollow circle down on the x-axis. And I can change the y-coordinate by dragging this point, hollow red circle, on the y-axis. And then when I decide that I'd like to collect that data set for distance and intensity, I can press the Control key and the decimal key. And it just saved this data, the distance of 1004 and the intensity of 0.00001, saved it, I believe, on the next page here in a spreadsheet. So here's the same data again, the 1004 and the intensity. And the thing that caused those to be loaded into the spreadsheet was back on page 1.4 when I pressed Control and decimal. So it's called manual data capture. So if I move a little bit closer to the airport, and I see that the distance is getting closer, so I'm about 500 meters from the airport, and the intensity is up a little bit. So let's say I wanted to save that. I'll press Control, decimal, maybe move a little bit closer. And each time I press Control decimal, then it's saving that data set, adding it to the spreadsheet. So I think in the Black Line Master, the students are encouraged to find about 10 data points. I don't think we'll bother to get that many. Hopefully you've got the idea here, but you could gather more than 10 if you wanted to. So when I jump to 1.5, this spreadsheet has been populated. And I think when I go to the next page, we're going to make a scatter plot of that data set. This scatter plot is in a different environment than the one we saw in the previous two activities. This is in a graphs window. So in order to create a scatter plot here, I'm going to press Menu and then change the graph type to scatter plot. So it's a little bit more work to create a scatter plot in this environment, but it's also more powerful. We have more flexibility. So I'll press Variable to bring up a list of the variables. I think I want distance for my independent variable. And I'll tab down to the next line and press the var key again. And I'd like intensity to be my dependent variable. And I don't see anything because I need a good viewing window. So if I press Menu and go down to Window Zoom and do a Zoom Data window, then we see something that looks like an inverse law, or actually it turns out it's an inverse square law. I'm running out of time, so I don't think I'll take you through the rest of this, but students could experiment on the spreadsheet or on this graphs window to find the equation that fits the data, and it turns out to be a constant divided by x squared, and by playing with the data, they can solve for that constant. So it's kind of a fun activity to experiment with an inverse square law. But in order to make sure we have time to get to some of the other activities, I think I'm going to hand off to Howard now, and Howard will show us a few more activities, both from Algebra 2 and from Precalculus.
Thank you, Ray.
Great. And as Ray is passing this over to Howard, we just want to remind everyone that even though we're still in the shared desktop, you'll have to go back up to the top of your screen, hover over that green tab that says that we're viewing Howard's desktop, and then access the Q&A window, the chat panel, and the participants panel. Thanks, Howard.
You're welcome. Well, the first activity I'm going to be looking at here is the exponential transformations activity. Again, this is available on the Nspired website. You can access it from the TI website. It's easy to get to, and Eric is going to give details on that. Exponential transformations. This is an activity that allows the students to experiment with playing with the transformation using a tool that Nspire has called a slider. And by changing the position of the slider, they're going to alter the equation. And then as they see what change that has on the position of the equation, they can begin to make hypotheses about what adding something at the end of the equation would do. And depending where we add or subtract numbers, how it's going to affect the equation. So in this particular activity, we've got again, a student document. Let me see if I can find where that one is. Exponential transformation student document. Looks like, I guess we have a little bit of lag here. Maybe I shouldn't be changing back and forth too much. This is a student document. Okay, it says move here, do this, slide stuff, look at questions, answer this question, what does that do? So let's go through that. First thing is, if we move this k value, what effect does it have? Well, if we move it up, we can see in a dotted line where the original function is, and we see in a solid thick line where the new function is. So we can begin to make a hypothesis. Oh, okay, I think that when I add a number, it slides it up. When I subtract a number, it looks like it slides it down. And again, as Ray mentioned early on, this is the action consequence model, that we're taking action on the mathematical objects, and we're observing what the consequence is. And because it's so immediate, we can make a hypothesis before we take action and say, I think that it's going to do this. Now let's find out if it really did it. Oh yeah, it did it. Or no, it didn't. If it didn't do what I think, then let's explore. Why didn't it do that? And that's where some of the very meaningful teaching and learning can take place. Okay, so we saw that adding a number there, it does a translation in the vertical direction. So if I make k equal 2, where will point 0, 1 be moved to? Right, if we were here, 0, 1, I'm going to make k equal 2, where will this point be? Well, I think it slides it up 2, so I predict that will be at 0, 3. So let's try. Chun. Oh boy, I'm so clever. Other pages in this document explore other ways to transform. This is subtracting h from the variable itself. And notice how we could make, back here, we have the slider going up and down. Here, they position the slider left and right. I guess to make a visual sort of reminder that this change is going to translate the equation, translate the graph to the left or to the right. And it goes on. We've got 1, 2, 3. We've got 3 more pages, each with a different translation, a different change of the base equation. Here on page 3, we are, what are we doing? We're multiplying. We're multiplying the exponent by a constant. What if this is another kind of slider? Okay, we call this a minimized slider. And if you're attending these webinars, you're going to hear us talking about sliders. And when you see this thing, it's not obvious to you why we would call this a slider. It's because it's the class of thing is a slider. It allows us to change values of a variable. Regardless, it's a slider. I can click the up arrow to make it get bigger. I can click the down arrow to make it get smaller. So what effect does that have on the graph when we make it very small? Oh, when it goes negative, it flips over. When it gets very close to 0, looks like it doesn't allow me to do 0. It jumps right over 0. As I get a bigger number, here's the effect. And by guiding the students through this sort of activity and asking questions as they do it, you can get them to think about what these transformations on exponential functions might be. What did we do here? We multiplied the variable by a constant. And page 5, combining all of them. And it's a very good way to explore this sort of activity and give students a sort of kinesthetic feel for what the activity involves. That's the exponential transformations activity. Are there any questions, Eric, at this point that maybe should be answered?
Let's see. We had a question about the Common Core state standards.
Mm-hmm.
Let's see. And Kelly's question is, are these activities correlated with the Common Core standards?
I don't know. I imagine that someone is working on that if they aren't already collated. I know that they're collated with lessons in textbooks, and they're collated with existing standards. But I don't know if the work has already been done to index them to the CCSS.
Mm-hmm. And I believe they are. I think some of the correlation may still be developed on some of the older activities that were written before the Common Core standards, but there's definitely correlation. And Eric, hopefully you can show us some of that towards the end of the webinar.
Yes, we correlate activities according to mathematical practices, or I should clarify that. The teacher notes for most of these activities and anything that was written after the Common Core was in effect, the teacher notes contain references to the mathematical practices, and that's kind of a special section of the Common Core initiative talking about the habits of thought and mind that students should be engaged with across all levels of mathematics. And then, and I will show us at the end how to do a standard search to find activities that are correlated to specific standards in the Common Core. And I'll actually take this opportunity to ask a question to Ray, even though, Howard, I know we're looking at your activities here. But
okay. Go ahead.
Let's see. Mary had a question about the airport activity, and she asks, the data points on the scatter plot were generated from the given equation. Can you hide the equation from students so they can derive it from the data?
Yes, absolutely. It would be easy to modify that and hide the equation.
Okay. And that's probably a skill that we'll see towards the end in those the video tutorials.
Right.
Thanks, Howard.
The quick answer might be if you just right-click on something, you can usually bring up a list of attributes, and one of the possibilities is to hide that thing.
Yeah. For example, over here, if I do it this way, okay. Like if I come here, let's slide over this way. And as I get to this equation, it's going to say, what is it going to say as it hovers over it?
That one's in a notes window, so it may not happen there, but if you go down into the graph window, maybe hover over the ordered pair 3, 4.
Okay. And I'm trying to do it instead of with my mouse with the touchpad, just so.
And then
you know what? It's not active. I have to click there to make.
Yeah, there we go.
Probably be easier just to right-click with your computer on this software.
Yeah, but I'm trying to show them how it, with the touchpad, you can get over there. Okay, now I've got that, and I can press Control Menu, and one of my options there would be to hide it.
Perfect.
Great. And now that's gone. If I change my mind, I can undo that, and it comes back.
Yeah.
But yes, you have a lot of control over what appears on the screen. Okay.
Great.
So moving on.
Thank you both. Yes.
Oh, yeah. Moving on. Next activity, what is log? Log is one of those really hard to teach and hard to understand concepts for a lot of students because it's such a weird function. And this is an exploration that helps students at least grab, make guesses, try to figure out what's going on. So let's take a look at this. We've got an activity. We got a function there, 2 to the x. Well, what are the domain and range? What's the domain of this function? Well, looks sort of like it's defined for everything. I don't see any. I might be confused at first, thinking maybe is this a hole in the function? But no, that's just point p. But it looks like domain is all real numbers. What's the range? Well, it doesn't look like there's any negative numbers in there. So I'm going to guess that there's no negative numbers. And in fact, there's actually no zeros either. But you can see domain and range. And we're going to talk about how you do an inverse function. Inverse functions are done by reflecting over the line y equals x. And I have this cute little slider here that allows me to show the line y equals x. And now I've got a reflection of point P down on the other side of the line. If I were to grab P and move it, the reflected point moves along with it. And I can get an idea, what is the shape of that inverse function? Okay, I can also use this slider and show the actual function that reflected point would be on. And that's where we see, oh, here's that log. In order to get the function that point P prime follows, I need the log function. So there's some guided questions for that. For example, why do you think x has to be bigger than 0 when we have this reflected function? Introduce into the idea that we're reflecting because the domain and range were all real numbers, and then positive numbers. Then we flip those. So now the domain becomes positive numbers, and the range becomes all real numbers.
Yeah, but actually, we have an observation from Peter that hit on that same point. He says students might surmise from the graph that the domain is not all real numbers because they may mistakenly observe the steepness due to the exponential nature of the function to conclude that there is an asymptote there.
Up here, we may start going vertical.
I believe so.
Yeah, that makes sense. Yep, that would be a common mistake. You could adjust for that. You could zoom out. We could, probably not in this activity, but at some point you could show them. Let's zoom out, and you see, yes, it is going all over.
Mm-hmm. And that statement might be easier to process in the Q&A window. So I know it was a long one verbally here, but it is in the Q&A window.
Yeah, but we could adjust the window settings and show that, yes, it is covering all real numbers as we zoom further and further out. One of the interesting things in the student activity at this point, I think it's over here, it gives it a table. It says, okay, now we've got those functions, slide P around and find out, fill out the rest of this table, which is a very good sort of kinesthetic activity. The kid is doing the action, making a guess where it moves to, and then filling it out. And they tend to get much better understandings when they've done the activity themselves. Back to here, move to page 1.3, and it gives a question. Okay, we've got log base 2 is 32. We know there's a relationship between the exponential form of the equation and the log form of the equation. What does n have to be in order to give me the exponential form of this equation? Well, clearly, when n is 1, it doesn't work, because log base 2 of 32 does not equal 1. Okay. try 2. Still didn't work. Let's try 3. Hopefully the student will at some point make a hypothesis. I think it's going to be 5, because 2 to the 5th is in fact 32. And then they can see, yes, it works out. But again, the use of sliders to quickly change values as they're making guesses as to what the effect is going to be is very beneficial. And this one, similar idea. Solve the equation, log base 4, 256 equals n, and we can slide till we find it. There it is. And that's an exploration of logs. Okay. I'm taking a look at the clock and notice that I'm talking too much, so I'm going to move on to the next activity and try to go a little bit faster on that. Eric, should we take a break, or are there questions that need addressing at this point?
Nope, we've been taking care of them over chat.
Okay, very good then. Next activity I want to look at is the unit circle activity. I should start at the beginning of the activity. The unit circle activity. We've got a circle. Here's a circle. And again, we call this a slider, even though it looks like some up and down arrows. So we got the slider there. And we want to press the up arrow and see what happens. And this is sort of one of those unwrapping the unit circle ideas, where as you go around the circle, it tries to tie that motion into what a sine curve looks like. Okay, there accompany some questions. For example, if I press from here, if I press 3 times, what kind of triangle does that look like? If I press it, if I get to pi over 2, what values does that seem to have? Moving on, similar activity, looking at the cosine. Again with the slider, as we start going around the circle, what's the length of that blue segment? And it generates the cosine curve. Suggested activities, click the slider until you obtain a value of theta such that it's between pi over 2 and pi. Okay, so I'm over somewhere in here. Explain the placement of the line segments. Why are the line segments going below the x-axis now? Sometimes that's a hard thing for the students to get, to understand why this is a distance, but why is it negative? Well, it's because we're going backwards from the origin, or however you want to explain it. And I think a very good question is one of the last ones here. How would you explain to a friend how to graph this function without using technology? I think this makes it very clear where that value that goes into the cosine function comes from, but how do you explain that? And that's a unit circle activity. Sort of very quick, but I didn't want to run over in time. Eric, what do you think? Should we keep going, or should we head into wrap-up mode?
Maybe the next one for 3 or 4 minutes, if that's okay.
Okay, we'll take a look at the vertical asymptotes.
Yes, that'll give us plenty of time to show the online resources.
Okay, very good. One more activity here, exploring vertical asymptotes. Again, the philosophy of so many of these documents as they were designed is to allow the students to make a hypothesis, take an action on a mathematical object, observe the consequences of that mathematical action, and based on that, try to come to an understanding of the math underneath it. So we want to look at vertical asymptotes. Here we have 3 sliders, A, B, C, And they're controlling this function, y equals c over x minus a over x minus b. As we change the value of a, what effect does that have on the function? You see I'm clicking the slider for a to make it bigger, to make it smaller, and the student can very, very quickly see it's changing where one of those vertical asymptotes lies. Same thing for b. Changes the vertical asymptote, changes the vertical asymptote. How about c? C is going to do what? Changes the spread of the function in a sense. And the document goes on with, what, 3 explorations of asymptotes. And then the interesting thing is the question page that you can put in documents. The equation has, asymptotes where, discontinuities. This kind of question, these answers, we call it radio buttons because only one of them can be selected. And you can select it, this one, not sure which one, and I can check the answer. I can go to the check answers, and it says, nope, wrong answer. I could try again. Is it this one? Check answer, wrong answer again. Okay. Which is a very nice thing to put in the hands of the student. They can try the work. They can check their answer. They don't have to keep saying, hey, am I right? Look at this. How about this one? Is this right? Over here on the side, in this particular menu, you can see where in the teacher software, I've selected the correct answer. It's the removable discontinuity at x equals -6, because this function would be the same as the function x minus 3, except for that one point at x equals -6. There's another type of question document. Here's some more explorations. Here's another type of question document. Notice that the checkboxes are square instead of round. This means I can select more than one, because it's possible more than one correct answer is in there. And again, you can check the answers, can clear the answers to let the next student try, and the teacher has the ability to choose